According to the classification of transducers by the transduction principle, the first one is resistive transducers. Now, as the name says, resistive transducers are those in which the resistance change due to the change in some physical phenomena. Assume that the resistance of the material is being given by R is equal to rho L by A. This equation that you all know. And R is the resistance, L is the length of the conductor, A being the cross-sectional area, and rho is the resistivity of the conductor material. Now, changing any one of this, if you change L, if you change A or rho, that can cause the change in the resistance that can be serving as the design basis of an electrical resistive transducer. There are four types of resistive transducers. They are potentiometers, strain gauges, thermistors, and RTDs. Now coming to potentiometers, the potentiometers are used for voltage division. They consist of a resistive element provided with a sliding contact. The sliding contact is known as wiper. The contact motion can be linear or it can be rotational or it can also be a combination of both. The combinational potentiometer have the resistive element in helix form and they are known as helipods. Now the following figure shows the rotational potentiometer and linear pod. The resistive element of pod, as you can see in the diagram, they can be excited either by DC or AC voltage. Pod is a passive transducer since it requires an external power source for its operation. Consider a translational pod as shown in the figure below. Now, as you can see in the diagram, there are certain terms which is being marked there. Let xi be the total length, xt be the total length of the translational pod. Xi be the displacement of the wiper from its zero position. Ei, E0, they are input and output voltages respectively. And Rp be the total resistance of the given pod. Then the output voltage under ideal condition can be observed, can be represented by the given equation. Now coming to strain gauges, it's yet another resistive transducer that will convert mechanical elongation and compression into a resistance change. When a metal conductor is stretched or strained, as we all know, there will be change in resistance because there will be change in length, there will be change in cross-sectional area, and also there will be change in resistivity of the conductor. And because of this piezoresistive effect, we call this piezoresistive effect, and because of this, the resistance strain gauges are also known as piezoresistive gauges. They are used for measurement of strain and associated stress for stress analysis. And further, they can be used in load cells, torque meters, diaphragm type pressure gauges, etc. As secondary transducers. Now let us see the gauge factor associated with the strain gauge. Gauge factor is first of all defined as per unit change in resistance to per unit change in length. Now consider a strain gauge made of circular wire. Let the parameters associated with the circular wire be L being the length, A being the area, D is the diameter of the wire, and rho be the resistivity. And these parameters have been considered before the wire is being strained. Let the resistance of this unstrained gauges R is equal to rho L by A. Similarly, assume that you are applying a stress S to the given unstrained wire. Now this produces a positive strain causing the length to increase and area to decrease as shown in the diagram. Assume delta L as a change in the length, delta A change in the area, delta D change in diameter, similarly delta R change in the resistance. Now in order to find out how R depends upon the physical quantities associated with the material, the expression for R is differentiated with respect to stress, and therefore we will get equation 1. Now we will divide this equation 1 by the equation of resistance, which is given by R is equal to rho L by A. Thereby we will get equation 2. Now it is evident from equation 2 that the per unit change in resistance means dr by R is due to three conditions. First one is per unit change in length, per unit change in area, and per unit change in resistivity. Area of cross section is given by pi by 4 t square. Now taking rate of change of area of cross section with respect to the tensile stress, we will get equation 2a. Dividing equation 2a with respect to area of cross section, we will get equation 2b. Now using this equation 2b to replace this term, in equation 2, one will get equation 2c. Now, the right hand side of equation 2c, the second term on the right hand side of equation 2c is replaced in terms of Poisson's ratio. Poisson's ratio is actually defined as the lateral strain divided by longitudinal strain. So, thereby you will get equation number 3. For small variation, the equation 3 can be written as an equation 4. Now, the gauge factor, as I have already defined, it is a ratio per unit change in resistance to per unit change in length. Therefore, the gauge factor can be expressed as an equation 5 that has been obtained by dividing equation 4 with delta L by L. Now, if the piezoresistive effect is negligible, then we can neglect the third term in the equation. Therefore, the gauge factor can be expressed as Gf is equal to 1 plus 2 into nu, where nu is the Poisson's ratio. Now, coming to the types of strain gauges, it has been classified into two. First one is the wire strain gauge, and the second one is semiconductor strain gauge. The wire strain gauge is again classified into three: unbonded type, bonded type, and foil type. Now, coming to the unbonded metal strain gauge, it consists of a wire made of copper, nickel iron alloys, which is stretched between 2 points in an insulating medium such as air. You can see that in the diagram. Wires are kept under tension, which means that there is no sag, there is no vibration, etc. Now, usually the strain gauge is connected to a bridge circuit. So, when the bridge is balanced, there is no output voltage, and when an external load is applied, the resistance of the strain gauge changes, which is causing an imbalance for the bridge. This will result in an output voltage, and this voltage which is produced will be proportional to the strain. Coming to the bonded wire strain gauge, it consists of a grid of fine resistance wire of very thin diameter. Now, the grid is symmetric to a carrier, which is usually a thin sheet of paper, bakelite or Teflon. Now, from the top of the material, it is covered with thin sheet of material in order to avoid mechanical damage, and the entire stuff is then adhesive to the specimen under study. Now, you may also go through the several features of the strain gauge. Now, coming to semiconductor strain gauge, it's a strain gauge which is having high gain factor, that is almost 50 times higher than the wire strain gauge. And this is very much desirable also, because as far as the sensitivity is concerned, the high gauge factor is very much desirable. Now, the working principle of the semiconductor strain gauge is based on piezoresistive effect. Piezoresistive effect, we have already seen the change in resistivity causing the change in the resistance. Now, the material used in semiconductor strain gauge are germanium and silicon. You may also go through the advantages and disadvantages of the semiconductor strain gauge.